So today's agenda is really about jitter, and what are some we have some causes of jitter, but really it's a lot about how to mitigate jitter and how to measure and analyze jitter, and that's where Mike comes in as well. So we are going to have a follow-up as to kind of going over more causes of jitter and a summary of this presentation. So as always, Lucy will send out the details. So basically how is jitter affecting your data transmission? So it's basically the deviation in the signal edges from their ideal positions, and this deviation has several critical consequences. You basically have sampling issues. You can have misinterpretation of the transmitted data or bit errors. You can have issues where jitter can also lead to missing or corrupted data at the receiving end, and Mike will go over that example as well. So the types of jitter in high frequency designs. Jitter in the time domain can be categorized into two types. So you can have random jitter and deterministic jitter. So in the frequency domain, jitter is referred to as a phase noise, and this is critical in high frequency applications like RF PCBs. So phase noise can cause interference between adjacent signals as well, both at the transmitter and receiver ends. So what causes insertion loss in high frequency designs? Insertion loss refers to the signal strength attenuation as it propagates through a transmission line, and the signal attenuation is caused due to several factors. First is dielectric loss, where the energy is absorbed by the dielectric material. Next is conductor loss, which is mainly caused by the skin effect and trace resistance. And the last one is radiation loss, where part of the signal energy escapes into the surrounding environment. So we're going to do a demo. Is that right? Is Vandana on?
Yes, sir. So,
okay, I'll pass it over to you.
Hi, everyone. We have the impedance calculator here today. This tool supports 82 impedance models with multiple geometries. We see that we have the uncoated, coated, and embedded microstrip here, along with the strip line. And for each of these models, you can choose single-ended or differential pair here. Let's go with coated microstrip in a differential pair mode and click on this. So the basic and the composite structures are displayed over here. Let's go with the basic model for now. The tool is also integrated with the signal loss, crosstalk, and the S parameter calculator, which I will be showing to you in a moment. We also have different units system available for the tool in the form of a drop-down. Here we go. This is the unit system. Let's go with mils for now and start entering the input parameters. Dielectric height of 3.348, for example. Let's go with 3.63 as the dielectric constant. A coating height of 1.5 mils. Coating height H2C is 0.5 here as a default value, but you can change it if you wish to do so. Then we have a coating height H3C. Let's go with 1.5 again. To calculate the trace width, we need to enter delta W here. Delta W is the difference between the top of the trace and the bottom of the trace. You can click on this help guide that displays a table that suggests delta W values based on their starting copper weight. You can use that as a reference. Let's go with 0.5 for now. Enter trace thickness of 1.45, a trace separation of about 7 maybe, and a target differential impedance. Calculate and click on calculate W, and the trace width will be calculated and displayed along with the other parameters here like the coupling coefficient, odd even impedance, mode propagation, delay, etc. We can also do the reverse calculation where we enter the trace width and calculate the differential impedance. Then we have the signal loss calculator here for the same chosen model. Let's go with 0.026 over here as the dissipation factor, a frequency of 10, 6 as the surface roughness, which is a standard roughness for a foil. And let's go with 2 inches over here and click on calculate loss. And the signal loss in the output and even mode will be calculated and displayed. Now we have the S parameter calculator here. Let's go with the source impedance 50 and the load impedance 50 again. And you can select the output type. Let's go with complex for now and click on calculate S parameters. Since we have chosen a differential microstrip here, we can see that it's a 4-port network. So therefore, we have 2 matrices over here is the output, the 4-port S parameter and the mixed mode S parameter. The characteristic impedance and the propagation constant in the odd and even mode, both are calculated and displayed. One thing you have to make sure is to use the S parameter calculator, you have to make sure to use the signal loss calculator where we have entered the frequency, which will be used over here for the calculations. Similarly, we have the crosstalk calculator for this model too. Thank you so much.
Okay, thanks, Vandana. Let me go back to the presentation. Can you see okay? Can you guys hear me and see the screen?
Yeah, we can see.
Okay, great. All right, so we definitely want to talk about strategies to minimize and mitigate jitter and insertion loss. So first and foremost, you have to select the right PCB materials for your application. And there are lots of materials around the world, and I think US manufacturers are becoming more accustomed to the overseas materials. So check with your manufacturer if they have experience with that material. Knowing the process steps of a material is critical in order to build a good circuit board. Anyways, I digress. So we want to first reduce the skin effect losses at high frequencies. So to do that, you can pick materials and copper foils that are specifically designed, for this purpose. Maybe they have a very low tooth profile and, therefore have been treated so you have good adhesion strength. But look at the type of copper foil that's being used in the materials, and I'm sure your fabricator can help you select that. If you don't specify anything, then you don't know what you're going to get. So as true always for PCB manufacturing, try and specify what you want without over specifying. So next, you want to select a substrate with high volume resistivity to minimize any leakage currents. And you want to choose materials, with a dielectric constant of less than 4 and a dissipation factor of less than 0.005.